continuing our discussion of free body diagrams and shear force and bending moment diagrams for this kind of a body. So we want to be able to now move on to a more complicated problem. Up to now we have seen distributed loads in which the distributed load looked this way. Now you have a triangular distribution in this case. The question is, what do we do here? Well, let's start. The question that we need to address is the following. Question is find shear force and bending moment at x equal to 1 and x equal to 4. So let's mark that point. X equal to 1 is somewhere here. Let's call that point P1. X equal to 4 is somewhere there. Let's call that point P2. Okay. So that distance is 1. This distance is 4. Okay. As usual, I'm going to draw a free body diagram. Our coordinate axis is going to be like that. I'm going to draw a free body diagram for this, and it's in the free body diagram looks like this. And this is 6 kilonewton per meter. That's this original height. This is 6 kilonewton per meter. The slope of this, since this length is 3, it is 2:1. The slope of this is 2:1. Okay, so we have all that set up. You know, in this particular case, again use common sense. And symmetry, and you can exploit symmetry. This means that AY equal to BY equal to half the load. Okay, and AX is 0. So it's pretty easy to see AY equal to BY equals 1/2 times, what's the total load? 6 times 3/2 plus 6 times 3/2. So that's this area. Of the triangle. That will immediately give me that AY equals BY equals 9 kilonewtons. Excellent. Now we start out and we want to actually do the next part. Part B is SF shear force and bending moment at x equal to 1 meter. I'm going to draw this free body diagram. Now this you have to be careful. That's 1 meter. We know that's 9 kilonewton. The distributed load starts out at 1, 2, 3, 4, 5, 6. So that's 6 kilonewton per meter. What will it end up? In 1 meter, how much will it drop? Notice it will drop by 2 because the slope is 2:1. So this one will be 1, 2, 3, 4. So it will be 4. And it's a straight line like this. So the distributed load looks like that. So now you can see why we need the centroid for trapezoidal figures. Whenever you have triangular loads, you have to worry about it. There's a shear force. There is the positive bending moment. Okay. So shear force and bending moment. So as usual, I'm going to do summation Fy positive equal to 0 gives me 9 minus V minus. Now I have to find the area, this area. How much is that? It is 6 plus 4 over 2 times 1. This is average height times base, because this length is 1. So this gives me shear force. If you compute it, shear force is 4 kilonewtons. What about bending moment? Summation around the origin equal to 0. So now I have to find out where is the centroid of this thing. The centroid will be here, the x component of the centroid. So this distance is xc, and xc, remember xc for a trapezoid. Now let me write that in green so you can see. So let me erase all this stuff. So let me write it in green. xc equals base times h1 plus 2 h2 divided by h1 plus h2 3 times. So h1 is 6, h2 is 4, and d is 1. So this will turn out to be 0.4667. So once we get the centroid, we can say this implies m minus v times 1 minus 6 plus 4, 6 plus 4 over 2 times 1, that's the area, times 0.4667, that's the centroid, equal to 0. So if I solve for m turns out to be 6.33 kilonewton meter. We are done. Shear force, bending moment. Now let's look at part C, which is to find shear force and bending moment at x equal to 4 meters. Let's draw the free body diagram again. By now you should have seen the drill, so it's always the same thing. 9 kilonewtons, there is 6, and here it drops all the way to 0, and then one more. So this height is 2 kilonewton per meter, because this slope is 2 and this length is 1 meter, and this is 3 meters. This is 6 kilonewton per meter, and this is all downwards. Okay, so again, summation of all the forces in the y direction, upward positive equal to 0, gives me minus v plus 9 minus 6 times 3 over 2, that is the area of 1, that's this one, minus 2 times 1 over 2, that's the area of the second one, that's that one, equal to 0. This is that. So this gives me V equals minus 1 kilonewton. If I take moments around the origin, m0 equal to 0 will give me 6 times 3 over 2 times 1.5. That's the centroid of this. This one is x centroid, first one. The centroid of the second one is here. And I want you to understand that it is this distance that we are interested in. We know how far that is. That's 1/3 of the base times this one. That's 1/3. So this one will be 11/3. That's the centroid of this region. It's 1/3 from this end, from the right angled end. So that's what we get. So now we are ready. Minus 2 times 1/2. This is the second area. This is A1. This is area of the second one. Times XC2 will give me times 4 minus 1/3. That's XC2. That turns out to be equal to 11/3. That's this one. Remember, it's the coordinate of the second one, not just the location. You can't just put 1/3. You have to measure from where you're doing the origin. That's why it's important for you to make sure you know where you're taking moments around. I'm taking moments around this point, so I need the distance, that distance. Okay, the distance from here all the way to there. So please remember that. Plus m equal to 0. So if you solve for m, sorry, minus, oops, I didn't account for everything. Minus v times 4 equal to 0. Oh my goodness, I forgot to draw the two crucial things, right? Don't forget that. If you do that, I will say that your free body diagram is not correct. I make the same mistake, but please remember, I caught it before I finished it. So same thing for you. Make sure you draw the right free body diagram. So once you've done that, then this means that I'm going to substitute for V from here. And so I will get M equals minus 1 times 4 minus 9 plus 9 plus 11/3, which turns out to be 3.667 kilonewton meters. Okay, so I want you to understand that we now have the shear force and bending moment at any particular location. It's a different matter if you want to find it for a lot of locations. You don't want to go on drawing different free body diagrams. That's where the shear force and bending moment diagrams come in handy. That's what we are going to do next time.